Hello and welcome to this course Design Practice 2 Module 21. We were discussing about actuators and sensor design, and in the last lecture we had extensively covered how pneumatic valves and thermopneumatic valves can be designed parametrically. We are now going to cover electrochemical valves, which are again non-conventional in nature, and then depending on hydrolysis of water and formation of a two-phase system, there can be a gating, ungating done in a small channel. I think I had illustrated this example last class in the last slide, when we are talking about electrochemically being able to make these bubbles and controlling the rates at which this bubbles get formulated, so that there is a forward or a reverse push to this particular gating device, which gates this micro channel right here. So, the channel has an inlet side somewhere here, outlet side in this particular zone, and so you can actually control the flow in this manner, or alternately you can create again a two phase here with a with hydrolysis and creating hydrogen oxygen bubbles, which can actually block the flow going through this constriction here, so that there is again gating or valving. Typically these kind of valves are used very often for microflows, because obviously we are just talking about a gas bubble and the mechanical strength involved in the bubble as the basic force of the valving action in the particular channel. So, in context of that, I had given a design problem here, where we talk about determining the energy required for generating electrolysis based spherical bubble with an approximate diameter of 28 microns. The reaction that was there, the hydrolysis of water reaction, is given in this particular equation. So, when we compare it to thermal bubble of the same size, obviously there will be differences, and that is what we have to compute, given some parameters including specific density of hydrogen or oxygen at standard temperature pressure STP, and also the surface tension of water, which is given again at room temperature conditions, enthalpy of formation of water, which is again given at the standard temperature and pressure conditions, and then some thermodynamic properties of liquid water, particularly both at 1 bar as well as 1 bar 25 degrees Celsius as well as 1 bar 100 degrees Celsius. This would be useful for computing the total work done in order to produce a thermally assisted bubble. And so, basically the comparison lies between what kind of energy would a electrolysis process uptake in comparison to a thermal process to formulate such a bubble, which will do this blocking action for the particular microchannel. So, let us actually start solving this particular problem. So, here we are assuming a contact angle of almost 0. You can understand that the bubble is sort of formulated just like a cylinder of the same cross section as the channel in which it is in, and with that kind of a contact angle, we would like to calculate the pressure inside the bubble, at least the difference in pressure between the inside and the outside. Okay. So, the pressure inside the bubble is estimated through standard equations for delta V in this kind of a situation. Delta V is twice sigma by R, sigma being the surface tension of the particular liquid water bubble interface. So, the sigma is already represented as 0.072 Newton per meter. This is borrowed from the question itself, and in this particular case, if we consider h to be the height of the channel, let us say this is completely the span over which the bubble needs to come out, so that there is valving of the flow. So, R in this case becomes h by 2. We assume the bubble to be centrally located and the bubble center to be the to be matching with the axial center of the channel. So, in this particular case then delta P is represented as twice times of sigma, which is 72 10 to the power of minus 3 divided by the height of the channel in this particular case of the, which is equal to the diameter of the bubble, is given as 28 microns. So, in this particular case the delta P can be 28 10 to the power of minus 6 meters times, again you have 2 here, okay, because obviously this whole h is 28 microns for the bubble to occupy the whole channel depth or channel size, and this is computed as 10 to the power of 5 pascals or approximately 1 bar for the bubble to hold. So, all properties are defined at 1 bar specific density, 1 bar pressure, and the specific density of the gas mixture, which formulates because of the hydrolysis process, need to be find out, so that we can do something to calculate the, already there is a enthalpy of the formation of water given as 285.83 kilojoule per mole. So, we want to calculate how much energy is needed, electrolytic energy is needed for formulation of this particular bubble. Okay. So, this is the enthalpy of formation. So, all the properties being defined at 1 bar, the specific density of the electrolysis gas mixture can be defined as the rho mixture equals the density of oxygen plus twice the density of hydrogen divided by 3. So, this is a sort of an average density, assuming the hydrolysis equation to generate both hydrogen and oxygen gases. This is a sort of a mixture density of both these in gaseous states. So, we can write this down as 1.429, which is the density of oxygen at the standard temperature pressure conditions. All the units are kg per meter cube, okay, plus twice the density of the hydrogen, which is written down as 0.08988 kg per meter cube divided by 3. So, this comes out to be, after calculations, 0.536 kg per meter cube. So, that is the average density of the mixture of gases, which is post electrophoresis, post electrolysis. And let us look at that. If this is the density of the mixture, we have a certain volume depending on what is the radius of the particular diameter. We should be able to calculate what is the mass of water that is needed to produce that kind of a bubble. Okay. So, the amount of water that is needed for generating the bubble is V rho mix, V being the volume 4 by 3 pi and the radius being 14 microns, 14 10 to the power of minus 3 whole cube, okay, times the rho mix, which has been calculated as 0.536 kg per meter cube, and this comes out to 6.2127 times 10 to the power of minus 15 kgs. So, that is how the M is defined, the total amount of mass of water which gets vaporized. So, having said that, we need to now find out what are the number of moles by dividing this with the atomic weight of water, which is H2O or 18, that how many kilomoles of molecules are needed, water molecules are needed to generate this gas bubble. So, this will give us an idea of what is the specific enthalpy of formation of the bubble. So, the mole number corresponding to the mass of H2O electrolyzed is 6.127 10 to the power of minus 15. This is in kgs. Let us make it in grams. Okay, 10 to the power 3 divided by 18 grams. H2O has an atomic weight of 2 plus 16, 18. So, that is how much is the weight of 1 mole H2O. So, therefore, this number comes out to be 0.34 10 to the power of minus 15 kilomole. Let us calculate the energy required for making the electrolysis bubble. So, the energy required for creating the electrolysis bubble is the mole number times the enthalpy of formation of water So, that is 0.34 10 to the power of minus 15 times of 285.83 kilojoule per kilomole. This is the enthalpy of formation per kilomole, and this comes out to be 97.2 10 to the power of minus 12 joules. So, so much amount of energy is needed for electrolytically formulating the bubble in the particular channel. Now, let us look at the thermal generation or thermal aspect and what is the kind of energy needed for the thermal aspect, and then we will try to calculate some efficiencies, particularly the electrochemical bubble formation efficiency and the thermal bubble formation efficiency. So, let us suppose at the standard temperature pressure condition, the specific volume of water vapor is reported as 1.0029 10 to the power of minus 3 meter cube per kg. The specific volume of water, this is at STP, standard temperature pressure condition, at 100 degrees Celsius and 1 bar pressure is reported here as 1.673 meter cube per kg. And these are from the stated question earlier. So, we want to calculate in the size of the bubble and the volume of the bubble, which is calculated before, assuming the radius to be about 14 microns, what is going to be the total amount of mass of water, assuming thermally actuated mechanism where bubble gets formulated and assuming a specific volume at the boiling point of water, that is 100 degrees Celsius, to be 1.673 meter cube per kg. So, obviously, this is going to be different than what the mass was of the electrolytic bubble. So, let us see what is that difference. So, here the mass becomes equal to the volume by the specific volume, and the volume here of the bubble again is the same, 4 by 3 pi r cube, and the specific volume in this case is 1.673. So, this comes out to be equal to 6.876 10 to the power of minus 15 kgs. So, this is somewhat different than what this other value was 6.127 10 to the power of minus 15, and that is because the mechanism of bubble formation is completely different. So, you can say that in the gaseous state, the energy storage is a little bit higher than what happened in the electrochemical case, and because of such a difference, there will be definitely a difference in the overall efficiency when we consider the expansion process and the bubble formation process. So, with this kind of a mass of the thermal bubble, okay, let us ignore all the other heat losses and let us compute what is the energy required for making such a thermal bubble. So, ignoring the heat losses, the energy required for making a thermal bubble is delta U thermal, which is equal to the mass m times of the internal energy at 100 degrees Celsius minus the internal energy at 25 degrees Celsius. So, obviously, the internal energies are different at both the temperatures, and you are going from the room temperature STP to 1 bar 100 degrees Celsius for the thermal bubble to be formulated. So, there is obviously going to be a difference in the internal energy because heat is being added to the system to formulate the gas state. And so, if we consider the mass that we calculated in the earlier equation through the specific volume term, that is 6.867 10 to the power of minus 15 kgs times, if I looked at U2 at 100 degrees Celsius has been given in the question as 2506.5 kilojoule per kg, I am sorry, kilojoule per kg, and U1 at 20 degrees Celsius has been given as 104.88 kilojoule per kg. So, I am going to just outlay these two numbers here, 2506.5 minus 104.88, and I am left with 1.64 times of 10 to the power minus 8 joules. This of course is a number in kilojoules, so we will just multiply it with 1000 to convert the equivalent joule number. So, this is what the thermal energy of the bubble would be when it gets formulated from 1 bar standard room temperature to 100 degrees Celsius 1 bar pressure. So, in both cases obviously an expansion work has been done because even if it is a boiling phenomena and generation of a vapor state, the bubble has to nucleate at some point and slowly expand to come to that 28 micron size. In the similar manner, in electrolysis as well, it has to nucleate at some center around the electrode, probably where the electrons are being pumped in, and grow in size eventually against the delta P pressure. So, some amount of work is needed to overcome that pressure and maintain the two phase condition so that the bubble can expand in size. So, let us look at that work done in this particular case. And so, if I looked at in both the cases, that is the thermal and the electrolytic case, the expansion work done by the bubble so it can be written as again the integral PdV, where P is really the pressure difference across which the bubble is expanding, and you know that that pressure difference delta P is already represented as a function of the bubble radius. So, more is the radius, lesser would be the delta P and vice versa, and it is also dependent on the surface tension. So, in this particular problem, if we assume the bubble to nucleate as a spherical bubble and formulate generally a zero contact angle overall occupancy within the channel, the spherical volume being 4 by 3 pi r cube, the dV in that particular case would be 4 pi r square dr. Okay. So, we want to just compute the W here by representing 2 sigma by r 4 pi r square dr integral, and r is obviously expanding from 0 to 14 microns. 14 microns is the final radius where the contact angle is almost 0. So, we are assuming that the contact angle is 0 as the bubble expands, and probably it may come from a flat electrode spanned over a certain length which would generate this bubble. from the electrode surface onwards. So, in this particular case, if we wanted to substitute all the values, we have the surface tension is 72 10 to the power of minus 3 Newton per meter, and obviously the r goes away here, and we are left with a 4 pi expression coming out of the integral times the value of the integral between 0 and 14 10 to the power of minus 6 meters. This is r square by 2. So, when we calculate this value right here and multiply, the overall number that comes out here for the total amount of work done is 1.772 10 to the power of minus 10 joules. So, that is what the expansion work is when we talk about electrochemical or even thermal bubble. So, a thermal bubble is also supposed to generate from a sort of a flat surface, so that we can assume the bubble to have 0 contact angle, okay, just as we are generating the electrochemical bubble. And so, let us now have a difference in comparison between the different efficiencies, that is one of the electrochemical process and one of the thermal process, and try to realize what all are those differences. So, the maximum efficiency of the electrolysis bubble in this particular case can be written down as, let us say we call it eta electrolytic. So, this is the work of expansion divided by the total amount of work of expansion plus the change in the electrochemical state of water, or the internal energy generated because of the change in electrochemical state of water, which is because of the enthalpy of the reaction. And when we calculate this number, it comes out to be 1.772 10 to the power of minus 10 divided by 1.772 10 to the power of minus 10 plus this delta U electrochemical, which we calculated earlier in this particular expression, and we found this to be 97.2 times 10 to the power of minus 12 joules. So, we put this value back here, 97.2 times 10 to the power of minus 12 joules. And similarly, if I wanted to calculate the maximum thermal efficiency, let us look at that number. The maximum thermal efficiency of the thermal bubble. So, we have N thermal max is W by W plus delta U thermal. Again, in this case, the work of expansion being same, the only difference which would happen is what amount of thermal energy is being generated, and that value has again been recorded here as 1.64 10 to the power of minus 8 joule. So, 1.64 10 to the power of minus 8 joule, and if we compare these efficiency values, so the efficiency for the thermal case is computed as 0.51%, and that in the electrochemical case or electrolytic case is 64.59%. So, obviously, the electrochemical efficiency is more in comparison to the thermal efficiency. So, we can say eta electrochemical is quite high in comparison to the thermal efficiency. So, one can think of this actuation scheme, electrochemical actuation scheme, to be better than simply a thermal scheme of formulation of an actuation mechanism, which would create a gate to move forward or backward. And one of the reasons why electrochemical may be showing better efficiency is that if we compare the internal energies in the case of formulation of a bubble thermally and electrochemically, they were very different in nature, and so that kind of gets expressed into the final efficiency equation. So, we will now try to go ahead and do some other kind of schemes for doing actuation. There is, for example, this capillary force valves, which are again actuated through something called a electrostatic double layer based actuation mechanism. It is also otherwise known as electrocapillary effect or electrowetting effect, and it changes the surface tension between two immiscible conductive liquids or between solid surface and a liquid by varying their potential difference. So, the surface tension equation that is provided because of a change in the overall dual layer aspect, the electrostatic dual layer aspect, is given by sigma equals sigma 0 minus C by 2 V minus V 0 whole square. C is the capacitance per unit area of this particular spherical bubble, sorry, the cylindrical bubble, and particularly the capacitance of the double layer of charges. We can assume these ends to be lengthwise minuscule in comparison to the overall length of the bubble. V is the applied potential across the liquid interface. So, basically the difference in potential between the both the electrodes, the positive and the negative electrodes, is V. Sigma 0 probably was the initial surface tension, and the sigma is the final surface tension when V potential is applied over and above V 0. So, as the potential is increased between both surfaces of the bubble, that is surface 1 and surface 2, obviously there is going to be a difference in the surface tension, and because of the difference in surface tension there would be migration. So, that generally the bubble moves towards the lower surface tension. So, this is a way to sort of guide a bubble and actuate again valving through in microchannels, in microflows, through just creating a potential difference. There is also a thermocapillary effect which can be used sometimes to do actuation. It is caused by temperature dependence, just as you saw the charge dependence and change in surface tension. There can be a temperature difference across the profile of a bubble, and you know that as the temperature increases the surface tension decreases. Okay. So, it reflects a sort of the difference in the surface energy. So, at higher temperatures the molecules of the liquid would move faster, their attractive force becomes smaller and vice versa, and because of such a difference in the surface tension, again there would be movement from the cold zone to the hot zone, and generally the bubble would try to move towards the hot zone because the surface tension is lower, and this pressure gradient would be good for actuating again a bubble in place, so that there can be obstruction of flow in a suitably designed actuator. So, when we talk about such microvalves, there are many such actuation schemes which are available. You saw that there is a thermocapillary effect, there is a electrostatic capillary wetting effect, there is also thermonumeric effect or numeric effect, and then electrochemical effect, and these all are different ways of performing actuation for which suitable designs can be initiated to do this basic phenomena of valving. So, I think I have gone through some of the very critical aspects of microvalving. I would like to close on this particular module. In the next module probably we will take up another section of where actuators are highly needed, which is microflow causing devices or micropumps. So, I am going to end this module now. Thank you very much.